Okay, so you should have already developed your own rules for position versus time graphs, but I just want to go over a few of those rules and then this one big rule that's really important. So I'm just going to start with the position versus time graph. Oh, let's start with this one. Looks like this. Okay, you should have noticed here that we have zero slope, and zero slope means zero motion or zero velocity. Okay, so that's a pretty easy one. Another one, something that looks like this. Okay, here we have a constant slope, and a constant slope means the object is moving with a constant, or sometimes this is called uniform velocity. Okay, so that's like rule number 2 there. Also, you can see here that the slope is positive. So the slope is positive, which means that that rate of change is positive. Okay, so the slope is positive, which means that the object is moving in the positive direction. Now, on the flip side, if we had seen something like this, this is still a constant slope or constant non-changing slope, which means a constant velocity. But notice now that the slope is negative, which means that the object is moving in the negative direction. Okay. Let's see, another one that you could have seen. Or another thing that you could have noticed here, position versus time graph. Like we've got that, and then we've got like this, okay? The greater the slope, so here, the greater the slope represents a greater velocity. It's still constant, okay? But it's just a bigger slope, which means a greater velocity, which means that the object is covering more distance per unit of time, okay? Here we have a smaller, more shallow slope, and that means that obviously the object is moving slower, okay? Another thing also to point out here is notice like that y-intercept. That y-intercept represents the initial position, So if I had something like this, this object is starting at the 0 position, whereas this object is starting at like positive 1, 2, 3, 4, all right, whatever units, positive 4 initial position. So that's helpful. Then the last thing that I want to look at is if we have something that looks like position versus time graph. We have something like this. So notice here we have a changing slope. Our slope is not uniform, it's not constant, which means that the velocity is changing. And we're going to learn a term for that later, which is acceleration, which you should be somewhat familiar with that. That means the object is speeding up or slowing down or even changing directions, okay? So that's a non-constant changing slope. And you can see that the slope is changing if you draw these tangent lines to that curve, those tangent lines, and you can see that the slope of the tangent lines getting steeper and steeper, which means in this case the object is speeding up in the positive direction, okay? So if you look here, if you look back, you can kind of see a theme. Slope, which means 0 velocity. Constant slope, which means a constant velocity. Positive slope, which means we're moving in the positive direction. Greater slope means greater velocity. You can kind of see a changing slope means a changing velocity. The big rule that we need to remember about position versus time graphs is that the slope represents the velocity of the object. And this is for position versus time graphs. Eventually, we're going to get to velocity versus time graphs, and that's a little different. Okay? So, a couple things. Remember, this one right here, huge. The slope represents the velocity when we're dealing with position versus time graph. So let's just look at an example, okay? Kind of work through this really quickly. So we have a position versus time graph of this running dude, okay? You can see that the running dude starts off at the 0 position, and see, here he is right there, 0 position. And then this represents like the 10-meter mark and the 20-meter mark and the 30-meter mark and so forth, okay? So we want to describe the motion of the dude for the first second. And I'm telling you right now, this is not realistic, okay? So for the first second, that's this part right here, okay? And you can see we have a constant positive slope, which means that for the first 1 second, the guy is moving with a constant positive velocity. So he's moving off with a uniform speed or velocity in the positive direction for the first 1 second, okay? You could even include his velocity, okay? If you think about this, rise over run, we're rising up 20 meters here. We're running for 1 second. Well, we know that slope, you can say, is delta y over delta x, or you could say that that is rise over run. And so 20 divided by 1, that would be positive 20 meters per second for that velocity, for that first 1 second. Okay? There's that equation. My picture kind of covered it up. 1 to 2 seconds. Okay, well, if we look at 1 to 2 seconds, from here to here, this part right here, you can see that there's 0 slope. 0 slope means that the object is not moving for that second. Okay, 0 slope, 0 velocity, right? For the third second, let's do the color. So for this second right here, from 2 to 3 seconds, you can see that the slope is constant and the slope is negative, which means that the object is moving with a constant negative velocity. Now, just looking at it, it doesn't look as steep as the guy running in the first 1 second, okay, which means that he's not moving as fast. And we can actually calculate that slope or that velocity. So we're going to do, we're going to go down here, and that's going to be 10 meters, and then we're going to run here for 1 second. So here, the velocity is only negative 10 meters per second. So he's not moving as fast, and the negative represents the direction. Think vector. The negative represents the direction. He's moving in the negative direction or the backward direction. So he's moving forward here at a constant positive velocity for the first 20 meters. He stops for a second, and then he's going to move back to the 10-meter mark, okay? And so forth. So I think we got the idea for that. I want to point out a couple of other things. Number 2 says, what are the displacement and the average velocity of the dude for the entire 4 seconds? Okay. Now, remember, displacement is that vector quantity. To find the displacement here, you could do it either way. you could do the final position minus the initial position, or you can add up all of the initial or all the individual, that's what I'm trying to say, individual displacements, okay? If you use the final position minus the initial position, you can see the final position is 40. The initial position is 0. So 40 meters minus 0 meters, that is positive 40 meters. Again, you have to include that direction, okay? It's displacement, vector quantity. Positive represents the positive direction. Or you could have done it like this. You could have said, okay, well, change colors here. This first displacement is positive 20 meters. This second is 0. This third displacement is negative 10. And then this fourth displacement is positive 30. So then you could add up those individual displacements. So positive 20, 0, negative 10, and positive 30, which would give you positive 40 meters. So either one works, okay? And then it wants to know the average velocity. Well, we know, I'm going to come over here, the average velocity is just the total displacement divided by the total time. So that's going to be positive 40 meters divided by the 4 seconds, okay? And that would be positive 10 meters per second. Now notice that's an average for the entire 4 seconds. That doesn't tell me how fast he was going during the first second or how fast he was going during the third second. It's an average, okay? Let's see. Then it's asking for distance and speed, which the distance is going to be different than the displacement because the guy changed directions there during that third second. So the distance here, the total distance is just d1 plus d2 plus d3 and so forth, not accounting for direction because distance is a scalar quantity. So that's going to be 20 meters plus 0 meters plus 10 meters plus 30 meters, and that's going to be a total of 60 meters for the distance. It's total length of travel, okay? So the average speed, okay, again, don't need a direction there because the speed or distance is a scalar quantity. The average speed is just going to be his total distance divided by time, and that's going to be 60 meters divided by 4 seconds, and you can divide that out. Now, the only other thing I want to point out here is this instantaneous velocity. So we know the average velocity is that positive 10 meters per second. The instantaneous velocity is like the velocity at a specific point in time, okay? So here, this is really easy. We want to know the instantaneous velocity at the 0.5 second mark. So right here, 0.5 seconds, all you need to do, because this is a constant, whoop, hang on. Because this is a constant non-changing velocity, this is the slope. It's just the slope. So here, it's a little big, isn't it? To find that instantaneous velocity, find the slope at the 0.5 second mark. And we've actually already done that. And then that is the positive 20 meters per second. The only thing that gets tricky is if the slope is not constant, and we'll talk about that.